Good morning, everyone. Let's start on our next topic. So, today we'll basically discuss backtracking, and next lecture we move to branch and bound. Am I audible, please? Can somebody confirm?
Yes, sir.
Okay, thank you. So, this material for this lecture is from Horowitz Sahani book, section 7.5, and look at other links. Also, give me a YouTube link on my earlier recording, but this recording also I'll be uploading it. So essentially, if you look at a Hamiltonian cycle is a problem which we again look at in daily life. As we said, traveling salesperson problem is a very specific case of Hamiltonian cycle. So let's say I need to invite n number of my friends and I need to start from my house, go to each friend's house and come back to my house. And having visited one friend, you don't want to visit the friend again. Now there could be many number of ways, there could be factorial n number of ways where you can visit them. And so whatever number of cycles, so essentially the problem is defined as given a graph G, you start from some vertex, go to each and every edge and come back to the same home path. And that is what is called a Hamiltonian cycle. And primary requirement is once you visit your vertex, you don't visit the vertex again. Now we can start with, remember, any vertex has to be part, so is always a kind of a cycle. So I can have, let's say, starting from, I can say vertex 4, vertex 6. Let's say I have 5 vertices. I can say vertex 4, vertex 3, vertex 1, vertex 2, and vertex 5. So, or I can write the same cycle as vertex 1, a vertex 2, vertex 5, vertex 4, you come back, and then vertex 3, and then back to vertex 1. So it doesn't matter which vertex you start from, each vertex is covered. So it's not important from which vertex to start. So in general, we always start from first vertex, that is vertex number 1. For generality, but you can always start with any vertex and we always get the solution answer there. So essentially start with one vertex, you visit the all the vertices and finally come back to the starting vertex V1. So basically visiting n edges, n vertices means you visit n nodes and n plus 1th node is your own where you start from, and that is what a Hamiltonian cycle is. So a graph can have any number of Hamiltonian cycles, and TSP, the traveling salesman person, is a problem among all those Hamiltonian cycles. Whichever gives me minimum cost is what we call a traveling salesperson problem. So TSP is a Hamiltonian cycle problem with minimum cost. So we look at how do we find for a given graph, how do you find the Hamiltonian cycles, and we look at those. Just to make sure that we understand, let's look at the following graph. Does this graph of 8 nodes, does it have a Hamiltonian cycle? And if so, what would the Hamiltonian cycle be? Anyone would like to answer? Is there a Hamiltonian cycle in this graph? Arvind, Avinash?
Yes, sir.
Yeah, can you give me the Hamiltonian cycle in this graph? Starting from vertex 1, start from vertex 1, what vertices we should be visiting so that we come back to the same. Can I say 1, 2, 3, 4, 5, 6, 7, 8, and 1? Is this a Hamiltonian cycle?
No, sir.
No. Why? Why it is not?
2 is
Yeah, tell me why it is not.
8 to 1, there is no 8, sir.
Yeah, from 8 to 1, there is no access, and that's the reason this is not a Hamiltonian cycle. So let's look at what are the Hamiltonian cycles possible. So one is I can go with 1 to 8, 1, 2, 8, 7, 6, 5, 4, 3, and then back to 1. Or I can do another Hamiltonian cycle. I can go with 1, 3, 4, 5, 6, 7, 8, 2, and 1. Can anyone tell me, do you find any commonality between these two cycles? Are these two cycles same? Are they different cycles?
Reverse, sir.
Yeah, it is reverse. So look at, either I can start this way and go back, or I can do this way. So that means I can start either way and I get the same cycle. So both are same depending on how do I travel. So that's what we're basically talking about. So that means when you list a Hamiltonian cycle, we can always use this property in mind, and then with it. So look, in one cycle, 2 comes before, in this, if you look at this cycle, 2 comes before 3, and in this cycle, 3 comes before 2. And so whichever vertex comes before other one, in this, that vertex comes after the other. And we look at this property to compute Hamiltonian cycles. When you look at branch and bound other cases, this property will use subsequently, but both happens to be roughly the same cycle. Let's look at, does this graph has a Hamiltonian cycle? Dharna? Chandan? Does this graph has a Hamiltonian cycle?
Yes, sir.
Tell me, what is the Hamiltonian cycle?
1, 2,
Hmm?
3.
4, and then
So,
you can say 1, 2, 3, 4. After that, you come back to 2, which is not
2.
we wanted, because we
Okay,
don't want to visit the vertex again.
okay, sir.
So this graph, there is no Hamiltonian cycle. Any questions about this? What about this graph? Does this graph have a Hamiltonian cycle? If I start
Yes.
from, let's say, vertex 2,
It's sir.
Yes, sir. Yes, sir.
yeah, I can go with 2, 3, 4,
4,
5,
5,
1,
1.
2. So every graph may not have a Hamiltonian cycle. Do not assume that graph always has a Hamiltonian cycle. Every graph may not have it, and if it has it, there could be more than number of Hamiltonian cycles. In fact, in fully connected graph, you might have factorial n Hamiltonian cycles possibility. So our job is to find Hamiltonian cycle in a graph, and that's what we will basically look at. So primarily, Hamiltonian cycle, what we call is non-deterministic polynomial complete, basically means there is no algorithm available which will, following deterministic step, do this, do this, do this. Every step is determined, and then we can determine this in polynomial time. And that's what we call NP complete, and we discussed probably in last 2 lectures what NP complete, NP hard, and NP problems are. So since there is no polynomial time solution available, we will look at backtracking approach to find all Hamiltonian cycles. Remember, TSP could be one, there could be multiple TSPs. TSP is minimum cost Hamiltonian cycle, and Hamiltonian cycle is a complete graph. Now, graph could be directed, undirected, and we basically look at backtracking approach So primarily is we look at the solution vector, what is vertex first, x1, what is vertex x2, x2 does not mean 2, xi represent ith vertex. So vertex x1, x2, x3, it could be anything, but they cannot be all different. And if we have visited k minus 1 vertex, number, so k indicates number of vertices visited, and xk has to be from remaining one. So that will probably become a bit more clearer there. Let's say if we choose this, when I have chosen vertex x1, vertex x2, vertex x2. x2 does not mean vertex 2, xk minus does not mean vertex k minus 1. It is which vertex we are choosing at the k minus 1 slot. And that means our problem is having chosen first k minus 1 vertices, how do we choose the next vertex? And while choosing that, we have to make sure that we are able to come back to the first vertex if it is the last vertex we have come to. So you can probably look at, and as you said, you can start from any vertex, but for simplicity for algorithm, we say we start from vertex 1, and that means x1 is equal to 1. And we would say, once we visit the last vertex, we need to come back to vertex 1. So when we visit k minus 1, next vertex has to be such that this should be connected. So vertex v, that means there should always be an edge between vertex xk minus 1 to vertex xk. That is the only way we can choose the vertex xk. And that is what we look at. And once you choose the last vertex should be connected to vertex 1. So whichever my last vertex is, I should be come back to vertex 1. And that is what the key requirement is. That's what we seen in the previous case, that this becomes a criteria. So now look at just to example what x1, x2 probably would mean. So let's look at this graph for cycle 1. For this cycle, x1 is 1, x2 is 2, but x3 is 8. x3 is not 3. x2, our cycle is this. So this first vertex, this is second number vertex, and this third vertex we have chosen. So k is equal to 3. So my xk is 8. So k is 3 means I am using vertex. Actual vertex node is 8, but is my third vertex. And then my fourth vertex is 7. So x4 is 7. So point I'm trying to say is vertex xk does not mean k. It may be, it may not be consumed. K means choosing kth vertex. Kth vertex could be 2, 3, like in this case, my third vertex is 8, my fourth vertex is 7, and so on, so forth. And I see this confusion, so be very clear about kth vertex does not mean vertex number k. So this is vertex number 8, but this is on my path, third vertex. So this is for k is equal to 3, this would be for k is equal to 4, and you see that. Similarly, in the reverse, if we look at it is first vertex is this, second vertex is this, so second vertex is 3, third vertex is 4. Again, understand xk does not mean k mean kth vertex we are choosing, xk identifies the vertex, and that's the difference. So let's look how do we find, just a run down the process of backtracking, and then we see define an algorithm. So we start with vertex 1. So we initialize, say vertex x1 is equal to 1, and then we say my k is 1. Now I need to choose for next vertex, k is equal to 2. Now when I starting from 1, my choices are I can go to 2, I can go to 3, and I can go to 7. So my choices are second vertex, I can choose vertex number 2, I can choose vertex number 3, or I can choose vertex number 7. Let's say I choose vertex number 2. So I choose, let's say, vertex number 2. Having chosen vertex number 2, now what are my choices? I can go to vertex number 3, or I can go to vertex number 8, or vertex number 1. Vertex 1 is already visited, so we won't consider it. The choice is either we can go to vertex 3, or vertex 8. So my choice is when k is equal to 3. When k is equal to 3, my choices are 3 and 8. One I'm probably ignoring here. 1, 3 or 8. One is already vegetate, we can't consider. So let's say we choose x3 is equal to 3 and we choose that. So x3 becomes 3 and we choose that 3. Now for k is equal to 4, my choices are either vertex number 4 or vertex number 6. So my choices for k is equal to 4. When I say k is equal to 4, my choices are either vertex number 4 or vertex number 6. And let's say, okay, sorry, when vertex 4 from 3, I can go to 4, I can go to 6, I can go to 1, or I can go to 2 as well. So for vertex number 3, 1 is connected, 2 is connected, 4 is connected, 6 is connected. But look, 1 and 2 already vegetate. You can't vegetate them again. So we have to vegetate between 4 and 6. So let's say we choose x4 is equal to 4. And this is what we do. We choose x4 is equal to 4. So for k is equal to 5, my choices are only this or this because 3 already vegetate. So my choices are choose 5 and then I basically make x5. Continue this way. I say vertex number 6 will be only 6. Now when vertex 6 is chosen, what is my vertex 7? When I look at vertex 7, 6 I can go to either 3 or I can go to 7, and then x7 I have choices of between 3 or 7. 3 is already vegetate, so we choose 7. Now vertex 8, k is equal to 8. When I 7 vertex k is equal to 8, I can come to 8. But if I choose 8, can I come back to 1? Because it's my last vertex. Remember, from the last vertex, I should be able to come back to first vertex. And now if I choose 8, I can come from 7 to 8, but this path is not possible. So that means 8 cannot be chosen. And because 8 cannot be chosen, we start backtracking and go back to place where we made a wrong decision. Backtrack till you make a right choice. And you see, once you backtrack, you'll basically, from 1 you chose 2, now you chose 3, and that's what will basically, from 2 you chose 3, now you chose 2 to 8 and proceed. And that's how we'll basically proceed, and that's how things will work out. This how we'll basically proceed backtrack. So we keep backtracking, we remove 3, and then look at next choice from 2 was, remember from 2, when I have to choose on 2, so k is equal to 3, my choices were 3 or 8. When I chose 3, I have to backtrack because I couldn't choose 1. Now next I choose 8. So I backtrack here, choose 8, and then I proceed, and then see I'll be able to make it. And that's basically what we'll do in Hamiltonian cycle. So look what is happening in our graph. What is the process? Essentially, you look at what we're doing is we are first choosing the next vertex, any vertex we take, and then verifying is the vertex chosen the right one? Does it work for us? Because if I from vertex 3 I choose 2, does it work? I choose 4. So first we choose a vertex. So my algorithm has 2 steps. One is called next vertex. Identify which is one valid vertex which is not already chosen, and then see can we proceed with it. If it is the last vertex, make sure I have the S from 1 here, and this is what we'll do. So my algorithm will have 2 steps. One is the next vertex method, and other is the Hamiltonian cycle. And these are the 2 methods, Hamiltonian cycle part. So we'll define 2 methods and explain the diagram these as well. So look, sorry. What is next value? Assuming we have already chosen up to k minus 1 vertices and we need to choose kth vertices. The next value k means kth vertex. And what we need to make sure that when we choose kth vertex, there should be kth vertex cannot be among the vertices we have chosen so far. Because if it is there, that is no right vertex. So what we do is initially we set all xi to 0 and xi could be any value from 1 to n. Because xi could be 1, xi could be 2, xi could be 3. And so what we'll do, we will compute, we go iterate for each k 1 to n and come back to 1. That means we can always say xi, so kth vertex can, starting from 0, we can always say xk is equal to xk plus 1 remainder n plus 1. This will make sure that we can start from 1 to n and come back to 1. And the moment I get 0, that means my all choices are over and it's not going to work. And that is what primary part of the next vertex is. So go in infinite loop, for our loop, compute starting value for all xk 0, get the next vertex, and if it is 0 means we come back to exhausted all possible, that means no vertex can be found. So if you found a vertex, now make sure that there is an edge from previous k minus vertex to this vertex. And we are keeping adjacency matrix. Because we are keeping adjacency matrix, from k minus 1th row to kth column, is there an edge? That will be the case only if edge is there, this value would be 1, other value would be 0. So if there is a vertex exists from k minus vertex we have chosen to the kth vertex we are done, if so that edge exists, otherwise there is no point choosing k because we can't even proceed. Then check, is this xk vertex we have chosen, is it among remain so far chosen 1 to k minus 1? So start from 1, make sure it is neither x1 nor x2 nor xk minus 1, because if it is any of the one, we need to look at the next vertex. And that essentially what we do in this case. So check for each vertex. If any of the previous vertex is same as mine, that means I break from this for loop and come back to the next level here. If not, that means j has become basically k. Now I need to check if it is the last vertex. If k is equal to n, then there should be edge to 1 from n to 1. If it is not the last vertex, then I am fine. If it is not the last vertex, that means value chosen is correct. If it is the last vertex, I have to make sure that there is an edge to the first vertex. And that primarily what we basically do, and I'll explain this with an example. Having chosen vertex k, my main algorithm works like this. So start with basically saying Hamiltonian k means having chosen the kth vertex, does it follow in my path? So basically first thing you call is next value. Choose the next value, which is the kth vertex. Make sure this is not 0, because this is 0, that means there is no path, and then we need to return backtrack. Because we are not able to proceed further, backtrack, go back to previous one. And then we basically return from this and go to previous. If it's not 0, that means chosen some vertex. If it is the last vertex, that means we've chosen all the vertices, we can print a path, and I'll get the Hamiltonian cycle, 1 to n, print everything. And if it is not the last vertex, having discovered k, I should now discover k plus 1th vertex. So call this Hamiltonian cycle again with k plus 1 and continue. And do this till we basically meet all. The moment we meet all, we return and our job is done. I'll take the same example what we have taken, applying this and see. So look what I have done. For each algorithm, I have basically given a step. Next value meaning I said step n1, n2, n3, n6, n7, n8. And same is true for next the Hamiltonian cycle algorithm. A1, A2, A3. I have given all those steps. And we look at starting from this. So initially all values are 0. We start with x1 is equal to 1, and that is what we do here. And now we need to invoke Hamiltonian cycle 2. We invoke Hamiltonian 2, and in Hamiltonian algorithm, first thing we do is call next value k. So we are calling next value 2. And we start with all xi's are 0, and we demonstrate how the x value changes in this case. I'm doing the detailed explanation so that you can understand. It may be easy for me to explain, but I'd suggest you please go through it, work out yourself, take other graph and make sure you understand the algorithm. So now look what happens. We invoke next value 2, Hamiltonian cycle. So we come basically here. Now first step is increase xk. My k is equal to 2. Please note my k is equal to 2, and initially x2 was 0. So x2 becomes 1 now. x2 becomes 1. Now check, is x2 is equal to 0? This is what x2 becomes 1. Check, is x2 is equal to 0? This is not 0 because x2 is equal to 1. So this condition is false. So come to next place. Now see, is there a edge from x1 to x2? Now look, x1 is 1, x1 is 1, x2 is also 1, 1 to 1 there is no edge, there is no self edge, so that means this condition is false. So if the condition is false, go back to while loop again, all over again. So we go back to while loop again, increase k, xk was 1, 1 plus 1 percentage n plus 1, my n is 8, so xk becomes, x2 becomes 2 now. x2 becomes 2, and is x2 is equal to 0? We go to the next step here. Is x2 is equal to 0? No, because x2 is equal to 2. Now come to third step. Is, remember my k is 2, so k minus 1 is 1. xk minus 1, that means x1 is 1. x2, which is xk, is 2. Is there a edge from vertex 1 to vertex 2? Yes, there is an edge from vertex 1 to 2. That means this is true. Now we want to make sure that whatever visited is not in the previously visited list. So look at all previous visited vertex. All previous visited vertex. Is that visited vertex equal to 2? J is 1, x1 is 1, x1 is not equal to x2. So we'll go to the next value. And now j2 1 to k minus 1, k is 2. We'll take only one time. So now we come to this stage, and basically j becomes 2. J is equal to 2, yes. And that means we are out of this loop. And now check, is it the last vertex? K is 2, n is 8, k is less than n, so return. So means next value returns x2 is equal to 2. And we come back to our Hamiltonian cycle. So we come back to 2, j is equal to k, and this is true. And so we return the value basically x2 is equal to 2, and that's what we return, x2 is equal to 2. That's essentially what we are doing. And then we come back to Hamiltonian cycle. This is, look, this is my Hamiltonian algorithm. This is my next value algorithm. So xk, this is what we invoked. Now we look at the Hamiltonian cycle. We say xk is equal to 0, no. For k is equal to 2, x2 was 2. So this is not true. So now go to the step what is called A3. So this is not true. Come to A3. Is k is equal to n? K is 2, n is 8. So this is not the last node. So go further. So come to else. That means we have visited vertex 1, we visited vertex 2. Now find for k plus 1. So k plus 1 meaning we invoke Hamiltonian 3. And Hamiltonian 3, when we invoke Hamiltonian 3, first invocation is next value. So we next value k. So we invoke next value 3, and that's what we do. Now k is 3. Initially x3 is 0. So this would give me x3 is equal to 1. This basically becomes x3 is equal to 1. Now do is x3 is equal to 0, which is not true. That means I'll look at next one. Is xk minus 1 is x2. And what is my x2? x2 is 2. x2 is 2. And x3 is, we are saying 1. So is there a edge from 2 to 1, which is the case? And because there is the edge 2 to 1, now we look at, is that vertex visited? So for all the vertices, vertex number 1, vertex number 2, k is equal to 1. Now look, x1 is equal to 1, x3 is also 1. That means this condition succeeds. When this condition succeeds, already in the path, so we break from this for loop. We're breaking from this for loop and not from this do while loop. So we come back to this next xk. Now we break, so come back to xk again. So basically we break, come back to increasing xk. Now x3 or k is 3. Still k is 3, value is 1 so far. With this execution, xk becomes 2. Means x3 becomes 2. Is x3 0? No, it is not 0. So now, is there a edge? Look, x2 is 2, x2 is 2, x3 is 2, 2 to 2, there is no self edge. That means this condition is false. This condition is false. We come back to next station of the do while loop. This condition false. Now xk was 2, so x3 was 2 so far. Now x3 becomes 3. I'm in a lecture, 1 hour. So x3 becomes 3. And now go to same, is x3 false? x3 0, which is false. So look at now, next step. Remember k minus 1, k is 3. So add x2 to x3. What is my x2? x2 is vertex number 2. x3 is 3. Is there edge from 2 to 3? Yes. So this condition becomes true. Then I look at, is this vertex 3 visited among so far these two vertices? So for xj1, look at x1 is equal to xk, which is false. Then j's next loop is x2 is equal to x3, which is false. And that means my j becomes 3. My j becomes 3 here. And so that means I need to check, is the last vertex? K is less than n, k is 3, and n is 8. So that means I don't have to check with last vertex. So I return, so this returns x3 is equal to 3. And then we come back, proceed same way. And same way you can keep proceeding for x4, x5, something of that kind. So you proceed for x4, Hamiltonian 4, Hamiltonian 5, Hamiltonian 6. So proceeding, you'll basically come to a place, you can keep doing it. When you come to basically Hamiltonian 8, when you come to Hamiltonian 8, you'll see what would happen. Hamiltonian 8, my x8 would basically give me 8, and x1 is 1, and from 8 to 1 there is no edge. So Hamiltonian 8 would fail at this point. When it fails at this point, so we backtrack. We invoke this, it will basically fall at this, what I said, it will fail here, and then you keep returning back from Hamiltonian, the algorithms, keep returning till we come back to Hamiltonian 2, and in Hamiltonian 2, we have chosen first 3 which have failed. Now we look at the next possibility, keep increasing. x2 will become 4, x2 will become 5, because this is not there, x2 becomes 6, and finally you choose 8, and then you follow the cycle 1, 2, 8, and we'll get this cycle. This is how basically the algorithm works. So I recommend you to work it out yourself, because unless you work it out, it looks very easy to understand. So make your own graph, work it out, and make sure that you understand and follow the algorithm. The algorithm is very similar to M coloring of a graph. We look at the color problem. That means given a graph, can we color with certain number of nodes? And this problem typically used in a map. So if you look at a map of any country, let's say look at our India, we have about 28 states. It used to be 29 because J&K is no more a state, it became union territory. So it doesn't really matter. So our country looks like something like whatever. I'm not good at drawing this map of country, and we have different regions. We want to mark each state with a different color. Let's say this is red, this is blue, this is green, purple, yellow. So, and I want to make sure that two states which are adjacent do not get the same color. So that we can differentiate easily. When you draw the map of any country or a world or a region or a state, the district, no two adjacent districts or no two adjacent states should have same color. And that basically coloring problem. So essentially you can map to coloring problem which says put a graph such a way that two adjacent nodes of a edge. So if I have vertex A, I have a vertex B, these two nodes cannot have same color. And we looked at this problem before, and we can map to planar graph to this problem. And M colorability meaning what is the minimum number of colors you can find so that you can color this graph. And that is what is called M colorability. What is the smallest value of M which you can use so that you can, using that many colors, you can color the graph. And this is what called M colorability problem, and that number M is called the chromatic number. So look at the planar graph like a map of a country or map of a state or a map of a district. It has been found that it is proven that any planar graph like our map can be colored with 4 colors. We don't need more than 4 colors. For a long time, 5 was considered optimal, but recently it's proven that 4 colors are good enough. Now you can basically look at our coloring problem such a way that for each state, may mark it a node, and two states, let's say this is state 1, this is state 2, if they are adjacent state, so this is node 1, this is node 2, if they are adjacent, draw an edge. So our map, we can convert into a graph problem where each state becomes a node, and there is an edge between two states if they are adjacent. And thus we get planar graph problem, and essentially objective is M coloring. So algorithm would basically be something very similar what we did for our Hamiltonian cycle. And essentially what we are saying is, so if there are n states, for each state I need to choose one color, could be color 1, color 2, color 3, up to m colors, such that no two edges have the same color. Now look, if my state space, if my graph which I made has a degree of m, that means each node has maximum of m edges connected to it, then we can always choose m plus 1 colors to color it. Tree height is n plus 1, we look at, and how do we can do that one by doing a state space tree. How do you go with the state space tree? You start from basically look at, so let me repeat how do you go with state space tree. This is my root node. Then for first state, so my x1 is first state, I have m colors, color 1, color 2, color 3, color 4, up to color m. And then for I look at my variable x2, Second state, again I can have m possibility. Of course, I can't do this same color again, but I can do other. So look at each node, I have m out degree, and depth would be, because I have n states, so my depth would be 1, 2, starting from 0, 1, my depth would be n plus 1, and that's essentially what I'm saying. So if I build a state space for m coloring, I have an out degree of m. Each node would have m possible values for x. Tree height is n plus 1. That's what we are doing. So how do my algorithm counting works? It's very similar to our Hamiltonian cycle. First is the main algorithm. Find for given node k is equal to 1. We start with x1 is equal to 1, because we can start with any vertex. And then choose the next color. For k is equal to 2, k is equal to 3. So for kth node, find the next color. Make sure the color is assignable, like what we did in the next value. If we have colored all the nodes, print. Otherwise, call the m coloring, go to the next color. And that's what basically what you're doing. And this way we can color. And what is this is very equal to your Hamiltonian cycle. First we call next value, and we're calling next color. We make sure that next color is a valid color. Otherwise we backtrack. If you can't find a color, backtrack. Means return. If it's the last color, we are done. Or if you found a color, then find the color for the next node. And what is my next color algorithm? It is very similar to next value. Keep incrementing. Instead of n plus 1, now we are doing m plus 1, because we are coloring with m colors. And then check if no color can be found, that means back return. If I found a color, check this color does not belong to any of the node which is connected. Make sure that, and if it's the last one, I'm done. So it's very similar to that. Now look at, in this case, my time complexity. Next color, look. Now this loop, I am running n times. And this loop, I am running m times. Because for each value of k, at some point it can become 0. So this can at the most execute m times. And for each of the xk value, I am running n times. So time complexity of next color is order m into n. Understand this again. For each node, I can assign m colors. For each of the color, I am doing checking, is it any color from previous nodes? That means I do up to n checking. And that means the time complexity for next color is order mn. Now total how many nodes I have got? Remember, in a state space tree, level 1 I have one node, level 2, so this is root level 0, level 1 I have m nodes, each of these gives me m nodes. So level 2 I have m square nodes. At level 3, each of these gives me our m cube nodes. That means at level I, my number of nodes is m raised to power I. So total number of internal nodes is 0 to n minus 1, m raised to power I. And at each node, we're spending this much time, order m, from the next order algorithm. And that means, so my total time complexity is sigma for number of nodes. And for each node, I take this much time. So this basically give me m raised to power I plus 1 n. N can be taken outside. And this mi plus 1, 0 to n minus 1, where I can say I1 to n. I can add a value 0 and say still mi plus 1 minus 1. And we know this sum is m raised to power n plus 1 minus 1 upon n minus 1. Essentially what we're getting is this is equal to n into m raised to power n plus 1, or we get n into m raised to n, which is still a exponential time. But backtracking can give us some solution which is better than factorial multiplication possibility. So this is the time complexity time, M coloring. So what we have discussed today, We look at Hamiltonian cycles. We looked at M coloring of a graph, and we pretty much done with backtracking. In next lecture tomorrow, we look at backtracking still gives exponential time, but is there a way we can reduce our search space? Can we do work in less than this time? And tomorrow we start with discussing what is called branch and bound. Branch and bound primarily means can you find an optimal solution? Let's say an M coloring problem, if I know that I can color the graph with 5 colors, so if any state space tree give me 5 colors, I don't have to explore. Look at it in state space tree which can give me 4 colors. If so, keep proceeding, otherwise ignore the solutions. And that is what we look at. Can we limit our solution? So primary branch and bound is used when we're looking at optimization problem. Can we find the optimization answers? Like traveling salesman person, if one state space tree gives me cost of 100, then any other branch which gives me 100 or 101 or 102, I don't have to explore because I already got a solution for 100. I will look at only those branches which can give me maybe 99 or 98 or something of that kind. So essentially, we look at only those nodes which can give me better answer. They give me poor answer, I can ignore. And that primarily is branch and bound. So I am done. Again, request you to go through the exercise, work out yourself, run the algorithm, follow each step to make sure you understood M coloring as well as Hamiltonian cycle. If you have questions, please ask me. Otherwise, we'll basically stop it. Thank you.